Well, if we can take integrals of polar curves and find areas inside of a polar curve, we can take derivatives of polar curves as well. Now, if you go back to the parametric stuff we did at the beginning, in parametric form, where t was the parameter, we said the derivative of y with respect to x was the way that the y's change with respect to time divided by the way the x's change with respect to time. Polar is going to look really similar to that, and that is the way the y's change with respect to x is going to be the way the y's change with respect to the angle divided by the way the x's change with respect to the angle. So we got three things going on here, right? We've got how the y's change with respect to x, so that's just your plain old what is the slope of the curve at a point. The second one, how the y's change with respect to theta, that tells me that as the angles change, how much do the y's change? And the one on the bottom says as the angle changes, how much do the x's change? If you take them and divide them, you get how the y's change with respect to x. So we could, I suppose, come up with a formula. If we know that y is equal to r times the sine of theta, then we can use the product rule to derive this. So using the product rule, I would take the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of the sine is cosine, and so there's my y prime. So on the top of this formula, I'm going to write r prime sine theta plus r cosine theta. Okay. On the bottom, if x is equal to r times the cosine of theta, now derive that. And I get x prime equals, again, derive the first, keep the second, keep the first, derive the second, except this time when I derive cosine, I'm going to get negative sine. That's going to put a minus in between. So now the bottom of my formula becomes r prime cosine theta minus r sine theta. So you could memorize the formula if you want, but you realize that you can also get it just by taking the polar rectangular conversions between x and y and sine cosine and setting it up that way. All right, so let's take a look at an example that uses that formula. So I want to find the slope. So find the slope of the line tangent. Let's just call it the tangent. To r equals 6 plus 2 sine theta at theta equals pi over 2. Okay, so using that formula, we already know what r is, right? R is 6 plus 2 sine theta. R prime then is going to be 0 plus 2 cosine theta. All right, so if I throw that in the formula that we have up on the top, dy dx equals r prime, which is 2 cosine theta. So there's my r prime. And then I need to multiply that by the sine of theta, plus r, which is 6 plus 2 sine theta, r times the cosine of theta. That's my numerator. That's my dy d theta. On the bottom, I can throw it in that formula. My r prime is 2 cosine theta. All right, so there's my r prime cosine theta minus r, which again is 6 plus 2 sine theta, r times the sine of theta. Now, could I simplify this? Yeah, I could. And in fact, if I were going to use this for something else besides throwing in a couple of numbers, I probably would simplify it. But really, I just want to evaluate that at theta equals pi over 2. And if I go back to my unit circle, the cosine of pi over 2, that's the x-coordinate, is just 0. The sine of pi over 2 is 1. All right, so now I get dy dx equals 2 times 0 times 1 plus 6 plus 2 times 0. All right, down the bottom, 2 times 0 times 0 is still 2 times 0, minus 6 plus 2, and then the sine of 0 is 1. So now all you have to do is watch order of operations. All right? This first piece is 0. That's 8 times 0, which is 0. That's 2 times 0, which is 0. But this thing down here is 8, right? 6 plus 2 is 8 times 1 is still 8. So I get 0 over 8, which is 0. What that means is that the tangent is horizontal. And this graph is actually not centered at the origin. It's centered at 2 units above. But still, theta equals pi over 2 is the top of this, right? So it does make sense then that there's a horizontal tangent up at the top at pi over 2. So that's just a matter of throwing in formulas. All right, here's another way to look at this. Okay, rather than use the formula, what if I want to think of it a little bit more intuitively? So let's find the slope of r equals 2 sine theta at theta equals pi over 3. So we know how to convert things between x and y coordinates and polar coordinates. If you have something that's in xy form, you can replace the x with an r cosine theta, and you can replace the y with an r sine theta. All right. So then let's throw in the values. We know that r is equal to 2 sine theta, so let's replace that r with a 2 sine theta and that r with a 2 sine theta. So I get 2 sine theta. The cosine theta is already there. Replace that r with a 2 sine theta, and again, carry that sine theta along for the ride. All right, so basically what I come up with is that x is equal to 2 sine theta cosine theta, and y is equal to 2 sine squared theta. Hey, that first guy, that sine theta cosine theta, do we know a formula that could help us out with that? Isn't 2 sine theta cosine theta the same thing as the sine of 2 theta? So maybe that looks a little bit nicer. All right, so I've taken my x's and y's, I've converted them into polar form, and now I've got representations for x and y in terms of theta. Now, let's take derivatives. If x is equal to the sine of 2 theta, then x prime of theta, or dx d theta if you want to call it that, is going to be what? Well, the derivative of sine is cosine, so I'll get cosine 2 theta times 2, right? Don't forget the chain rule. If y is equal to 2 times, I'm going to write my sine squared theta as sine of theta squared, then y prime of theta is going to be 4 sine theta to the first times the derivative of the inside. Well, the derivative of sine theta is cosine theta. So I get y prime of theta is equal to, let me write this as 2 times 2 sine theta cosine theta. Oh, look at this. 2 sine theta cosine theta, we said before, was a sine of 2 theta. Carry down that 2, and now I've got y prime of theta equals 2 sine of 2 theta. All right, good. Now we're ready to assemble this together. So dy dx, how the y's change with respect to x on the graph, is going to be y prime of theta divided by x prime of theta. So the y prime is 2 sine 2 theta. The x prime is 2 cosine 2 theta. And look how nice that is. The 2's go away. And then sine 2 theta over cosine 2 theta, well, sine over cosine is just tan. That's an expression for the derivative in terms of theta. And now if you want to evaluate that at pi over 3, then you just need to say dy dx equals the tan of 2 pi over 3. What is the tan of 2 pi over 3? Well, where is 2 pi over 3 on the unit circle? On the unit circle, 2 pi over 3 is in the second quadrant. What are the coordinates over there? Well, it's got to be either a 1/2 or a square root of 3 over 2. Where is it? Is it way down the bottom or is it closer to the top? It's got to be closer to the top, right? If that's pi over 4, 2 pi over 3 is up there somewhere. So the x-coordinate is going to be negative 1/2. The y-coordinate is going to be square root of 3 over 2. So if you forget which one is which, think of where you are. If you were down closer to 5 pi over 6, then the x-coordinate would be greater. You're not. The y-coordinate is greater. All right, so take those two things and divide them. Take sine and divide it by cosine, and you realize you end up with negative square root of 3. And that's my answer. So there's another way to do it. Instead of using the formula, convert everything between polar and rectangulars. Once you get polar representations for everything, then derive the x's, derive the y's, both with respect to theta, and then divide them. All right, let's look at one more thing in this section, and then we're done. Length of a polar curve. If you can do length of a rectangular curve, then you can do length of a polar curve. Right, the length of a polar curve formula looks like this. I'm not going to go through and derive the whole thing. A and B will be my limits of integration, and I'll end up with the square root of r squared plus dr d theta squared. So this should look somewhat like a parametric form. And then over here, d theta. All right. How do I use this length of a polar curve? So suppose I want to find the length of r equals 3 plus 3 cosine theta on the interval from 0 to pi over 4. So I'm looking for just a small piece of this polar curve. All right, so r squared, let's work on the side for a little bit. R squared is going to be this term squared. So 3 plus 3 cosine theta squared, which if I expand that out will give me first term squared, 2 times the inside, and last term squared. And then dr d theta is just going to be 3 sine theta, except with a negative, right? The derivative of cosine gives me negative sine. So negative 3 sine theta. So dr d theta squared will give me 9 sine squared theta. Right, and this formula says then I should add together r squared and dr d theta squared. Let's do it. So the length of my curve will be the integral from 0 to pi over 4 of the square root of r squared, so 9 plus 18 cosine theta plus 9 cosine squared theta, plus the dr d theta squared, which is 9 sine squared theta. All right, this looks hopeful, right? If sine squared plus cosine squared equals 1, then 9 of them should give me 9, and this 9 and that 9 combines to be 18. So the length will be the integral 0 to pi over 4 of the square root of 18 plus 18 cosine theta d theta. All right. Now, I could actually do this analytically. There is a way to match up that cosine squared formula, the 1 minus cosine 2 theta over 2, 1 plus cosine 2 theta over 2, in order to come up with something that will give me a perfect square under that radical. And then when I take the square root, it goes away. At this point in this video, I don't think it's worth doing. So you can take this and throw it on a calculator. Let's see if I have an answer. I do. In case you're curious to know what the answer is, through math magic, it comes out to be 4.592. Okay. If you want an exact value, like I said, there actually is a way to figure out an exact value. Probably not necessary at this point, though. But that is how you find the length of a polar curve.